On the ACT, we will often be asked to find the graph of a linear inequality. So linear inequalities look very similar to linear equations, except now, in order to solve a linear inequality, we have a shaded region either above or below sections of the graph. So let's do several examples. I think that'll give us a good idea of how to graph linear inequalities and what the graphs look like. So let's take the first graph, y is greater than 1. So y is greater than 1. We know that if the line said y is equal to 1, we would simply have a line at y equals 1, and we'd be done. So because this is an inequality, and we don't want to include 1 in here because it does not say y is greater than or equal to 1, we're going to use a dotted line at y equals 1, because we don't include the actual value 1. And then what we're going to do, we want y to be greater than 1, so we're just going to shade in the part of the graph that is above that line. And that will be the graph for y is greater than 1. Let's move on to the second example, y is greater than or equal to x. So because we have greater than or equal to, we can actually use a solid line. And we know that y is equal to x looks like this if this were a linear equation. Because we are greater than or equal to, we can shade in anything above the line, and any of those values will satisfy the inequality here. So anything that shows up above this line will be a valid solution. Of course, anytime you are unsure, you can always test a point. So if we were to randomly choose the point -1, 1, then we would have y being 1. 1 is greater than or equal to -1. So we know that that would at least be correct. Let's look at the graph for the line, or for the inequality. Y is less than or equal to 2x plus 1. So in this example, we have a less than or equal to sign. So again, because we have or equal to, we can use a solid line instead of a dotted line. We know that for this inequality, if we were to convert this to a line, then we would know that the line has a y-intercept of 1 and a slope of 2. So we can draw it like this. Now we just need to shade in the appropriate area of the graph, and that's going to be anything that falls below this line. And that would be the solution to that inequality. What about the inequality -2y plus 4 is greater than 2x? So for this, we're going to treat this like a linear equation, and we're going to solve for y. So we'll solve for y at the bottom here. So we're going to subtract 4 from both sides. And then we're going to divide both sides by -2. And of course, when you divide by a negative number or multiply by a negative number when you have an inequality, you have to reverse the direction of the inequality. So now we're going to get y is less than -x plus 2. So let's graph the line y equals -x plus 2. And of course we use a dotted line because we have a less than sign here, not a less than or equal to sign. So -x, so our slope's going to be -1, and our y-intercept is going to be at 2. So our line will look something like this. And now we want y to be less than, so we can shade in the area underneath that line. Let's look at a compound linear inequality. So y is greater than x, or y is less than or equal to -1. So we know the line y is greater than x will be a dotted line that looks something like this. And then y is less than or equal to -1. We can use a solid line. And this is an OR equation. So that means if a value satisfies either of the two linear inequalities, then it's going to be a solution for the compound inequality. So y is greater than x, so anything above this line is going to be valid. And then anything, so y is less than or equal to -1. So anything below this y is less than or equal to -1 is also going to be a solution. So the only part that isn't going to be a solution is going to be this unshaded region that looks like a triangle that extends out forever. All right, last example, we have an AND compound inequality. So let's figure this out. So let's first rewrite the first part of that inequality. We're going to change it so that it's not -y, but it's +y. So we're going to get y, instead of greater than, because we're switching signs here, we're going to have y is less than -2. And then we also have y is less than or equal to x. That remains the same. So let's put both of these on the graph. So y is less than -2. We're going to have the dotted line at y equals -2. And then y is less than or equal to x. We'll have a solid line. And because it's an AND inequality, any solution will have to be valid for both parts of the inequality. So y is less than -2 would be down here, and then y is less than or equal to x would be below that line. So our solution will be anything that fulfills both of those inequalities, so it is this region right there.